This chapter is on metric spaces. In this chapter, we're going to generalize the concept of a space with distance. So we're used to usually thinking about the real numbers or the real numbers crossed with the real numbers, like the Cartesian plane, or maybe the real numbers cubed, the real numbers in 3 dimensions. And we kind of have a standard notion of distance within those 3 spaces. So we want to think about, basically what mathematics do we do there, and what does it mean for there to be distance? Like, what are the essential properties of distance, and what are its implications? So to start, the standard distance on just the real number line is, if we say what's the distance between 2 points A and B, then we could say that the distance between those 2 points A and B is the absolute value of A minus B. That would be sort of our standard, what's the distance between 2 values on the real number line. With that in mind, here is our generalization of the idea of distance on a set. So if X is a set, then D is a metric on X if D maps the set X crossed with itself to the set from 0 to infinity, in other words, to the non-negative real numbers. And when we say X cross X, remember that that's just things with the form A comma B in X cross X, so those are ordered pairs, such that for any X and Y in X, D of XY is equal to 0 exactly when X equals Y. 2, D of XY is equal to D of YX. In other words, its distance is symmetric. And 3, D of XZ is less than or equal to D of XY plus D of YZ. This is called the triangle inequality. And we'll sort of see where that comes from in a moment. So here is an example. Our example that we started with, just the distance between 2 points on the real line. Let's just verify quickly that that satisfies those properties above. So 1, is it true that the distance between A and B is equal to 0 if and only if A and B are equal to each other? So let's show that that's the case. If we're thinking about the absolute value of A minus B, then that is equal to 0 if and only if just A minus B without absolute values is equal to 0, and that's true if and only if A is equal to B. Okay, great, just by adding B to the other side. So good, we verified 1. How about 2? Well, is it true that the absolute value of A minus B is equal to the absolute value of B minus A? Yes, that is true. And now let's look at the distance between A and C. And this is a trick that we'll sort of do repeatedly when we think about the triangle inequality. We will subtract and add the middle term in. Now that, in absolute values, is going to be less than or equal to what we'd have in absolute values if we broke this up. So if we broke this up into the absolute value of A minus B plus the absolute value of B minus C, that is going to be greater than or equal to the whole expression in absolute values, because if we have anything, if either piece of this is negative, then of course this will be larger. If neither of the pieces is negative, then it's just going to be equal. And so that is showing the triangle inequality in this case, that the distance between A and C is less than or equal to the distance between A and B plus the distance between B and C. The term triangle inequality comes from the usual metric on r squared, what we normally think of as the distance between 2 points on the plane, which is given by the square root of y2 minus y1 squared plus x2 minus x1 squared. So just sort of seeing that in action, this is your usual distance between 2 points. In other words, the length of this line segment between those 2 points. And it is given by, here in absolute values, is the distance between y2 and y1. And here, the distance between x2 and x1. We don't need the absolute values really because we're going to be squaring each of those. And then just by the Pythagorean theorem, we know that, c squared is equal to, if this is a squared plus b squared this is b, and that therefore c, that distance we're interested in, is the positive square root of a squared plus b squared, which is exactly that. And this is called the triangle inequality because we've got this triangle saying that the distance between this point and this point plus this point, the distance between this point and this point, should never be less than the direct distance between these 2 points. So that's where the term triangle inequality comes from. Similarly, we define the usual metric on Rn. So R cubed would be 3-dimensional space, R4 would be 4 dimensions of the real numbers, and so on, to be the distance between the vector A and the vector B to be the sum of AI minus BI squared, all square rooted from I equals 1 up to n. And so we see that this is the same thing as what we have above in R squared. And if we're talking about 3-dimensional space, then just whatever the sort of straight line distance between those 2 points will be in 3-dimensional space, that's exactly what our usual metric is in R cubed, and so on. It's clear that the distance between 2 points is going to be equal to 0 if and only if the vectors are equal. In other words, they're equal in each of their dimensions, each of their components, and that the distance between A and B will be the same as the distance between B and A. This is symmetric. The triangle inequality is actually a little technical here. It's on pages 56 to 57 of our book. And I would consider this kind of proof really more of a real analysis type of proof. I know some of you have had real analysis. So feel free to read it over, but I won't ask you to do a proof quite like this. All right. So we saw the usual metrics for Rn, for the real numbers in n dimensions. However, there are many others. There are a few that we'll use often, and I want to talk about those. So one of them is called the taxicab metric for Rn. And here, we'll call that d prime for now. D prime of A and B, between the distance between the vectors A and B in the taxicab metric, is the sum of the absolute value AI minus BI over each of those components. So, for example, if we were talking about the distance between the point negative 3, 1 and the point 2, negative 4, the distance in x is going to be, negative 3 minus 2 in absolute values is going to be positive 5. The distance between those 2 points in the y dimension is going to be the absolute value of 1 minus negative 4. So that also happens to be positive 5 in this case. And so the distance between those 2 points is the sum of those absolute values, and it's going to be 10. So this is the taxicab metric, or sometimes called the Manhattan metric, and you can probably see why. So if you're driving down city blocks, you can't cut across the middle of, through everybody's houses and businesses and stuff. You need to go down the roads and streets, which may be arranged in sort of a grid-like fashion. So let's prove that this is a metric on Rn, on the real numbers in n dimensions. So first of all, the distance between 2 points A and B, AI minus BI, from I equals 1 up to n, is going to be equal to 0 if and only if the absolute value of AI minus BI is equal to 0 for every component. Why is that? These are non-negative real numbers added up together. Non-negative real numbers can only add to 0 if each one of them is 0. So this is for all values I, and this would be true if and only if AI is equal to BI for all I, and that is true if and only if the vector A is equal to the vector B. All right, so the distance between two elements in the set is 0 if and only if those elements are equal. 2, we want to show that this is symmetric. So if we look at d prime of a, b, that is, as we saw above, the sum of ai minus bi in absolute values. that is equal to the sum of bi minus ai in absolute values. And so that is d prime of b minus, or of ba. So yes, this is symmetric. And lastly, the triangle inequality. So if we want to look at, if we have 3 points, A, B, and C, then and we want to show that the distance between A and C is going to be less than or equal to the distance between A and B plus the distance between B and C. So that's what we want to show the triangle inequality. So to show that, let's look at the distance between A and C in this taxicab metric. As we saw, that's the sum of the AIs minus the CIs summed over n. And like we did before, we're going to do the same trick of AI minus BI plus BI. And so we're just sticking in a plus and minus right in that summation. And so now we've got that that's equal to the sum of AI minus BI. Actually, this is going to be less than or equal to the sum of absolute value AI minus BI plus BI minus CI, for the same reason that we discussed before, that if we think about, breaking up this sum, if each of those pieces is non-negative, then that's an equality. But if either of those is less than 0, then this whole thing is going to be strictly less than this. Okay, so now what is that equal to? That's equal to the sum of the AI minus BI plus the sum of the BI minus the CI, and in absolute values, and that is d prime of AB plus d prime of BC. So going through an intermediary point cannot shorten our distance. And that ends the proof, so we can celebrate with a shaded box or a W to the 5th or a QED or whatever we like. Okay, here's another metric for R to the N. This is the max metric, and this is just that the distance between 2 points is the maximum of the absolute values of the distances between their components. So this is similar to the proof above that this is a metric. It's also on page 59 of our book if you want to check it out. And then here is another metric. This is called the discrete metric, and this doesn't only work on R to the N, but it works for any set X. So for any set X, this will be a metric, and here it is. For all X and Y in the set X, the distance between X and Y is defined to be 0 if X is equal to Y, and 1 if X is not equal to Y. We'll certainly be talking about this metric more, or using it as counterexamples, or just using it for intuition at various points. So to get us just some familiarity with each of these metrics, which again we'll sort of revisit at various points, I'd like you to find the distance between the points A equals 5, negative 3, and B equals 2, 1 in the following metric spaces. So the usual metric, the taxicab metric, the max metric, and the discrete metric. So I encourage you to pause at this point and try those out, and then we'll talk about it together in just a moment. All right, so in the usual metric, so when we're thinking about the usual metric, that means that the distance that we're interested in is the straight line between those points. And we know that the distance between A and B is given by the square root of the differences of the components squared. So the x-coordinates 5 minus 2 squared plus the y, difference in the y, negative 3 minus 1 squared. So that would give us the square root of 3 squared plus 4 squared. So that's the square root of 25. And therefore the distance between A and B in the usual metric would be 5. What about in the taxicab metric? Now we're instead interested in just the sort of XY path between those 2 points. And so the distance between A and B in the taxicab metric is going to be given by the distance in the x direction plus the distance in the y direction. And so that's 3 plus 4, that's 7 in the taxicab metric. What about the max metric? Then the distance between these 2 points in max metric is given by the max of the sort of absolute value of the differences in the x direction and the y direction. So the maximum of 3 and 4 would be 4. So in the max metric, the distance between those 2 points is 4. And finally, in the discrete metric, the distance between the points A and B in the discrete metric, well, those points aren't equal, and therefore the distance between those 2 points in this metric is 1. Now we're going to look at some examples of metric spaces where the set we're interested in is not the n-dimensional set of real numbers, but some other set. So let's first consider the set CAB, and we're defining that to be the set of all continuous real-valued functions over the closed interval from A to B. There are different metrics we can define on this set. One of them is, let's call it delta of fg, is the least upper bound of the absolute value of f of x minus g of x, such that x is an element of the closed interval A to B. So if, for example, if A was -1 and B was +1, and we were talking about our set X to be the set of continuous functions over the closed interval from -1 to +1, then let's just pick 2 functions in there. Let's pick some very familiar functions. Let's say f of x is x squared and g of x is x. So yes, those are both continuous over this interval, so great. Then the distance between those 2 functions in this space would be, here is the interval from -1 to +1. We're only interested in that interval. What is the least upper bound of the differences between those functions, between the outputs of those functions? And we see that the largest it gets is, here is an output of 1, and here's an output of -1. So it would be 1 minus -1. It would be 2. 2 would be the largest distance between these 2 sets. So showing that this is a metric space is a homework problem, and there's 2 things to note in doing this. One is just, what's the definition of 2 functions being equal? F of x and g of x are equal over the closed interval a, b, if and only if f of x and g of x are equal for every value of x in that closed interval. So we actually don't care about what the functions are doing outside of that interval. They are equal in the set if they are equal over that interval. And 2, so the extreme value theorem, way back from Calc 1, says that if f is continuous over a closed interval, which all of these functions are, then f of x attains both its maximum and minimum over that interval. And since g of x and f of x are continuous, that means that the difference of those is also continuous. The absolute value of that difference will also be continuous. So why is that important? That's useful because we can sort of replace this least upper bound of the absolute value of f of x minus g of x such that x is in the interval. We can replace that with the slightly easier to think about just maximum of f of x minus g of x over that interval. So you can replace least upper bound with max, and that's just a little bit easier to work with. Here's another example. So some of you have had graph theory before, some of you haven't. If you haven't, no big deal. This is just a quick example just to tie it to another discipline. So a graph is a set of vertices and edges between vertices, so points and lines. If v of g is a set of vertices in a connected graph, then the distance between 2 vertices is going to be equal to the length of the shortest path between u and v. And that is a metric on the set of vertices of the graph. So a lot of the things that we'll learn about metric spaces can be applied in the setting of graphs. So for example, here's u, here's v, the distance between u and v, the length of the shortest path between those points. We could do different things, like we could do that, and that would be a path, but there is a shorter path, and so we could go 1, 2. The distance between those 2 points on a graph is 2. So that definition of distance on a graph does give us metric space. Here's another example. So in information theory or coding theory, the Hamming distance between 2 strings of equal length is the number of positions at which the corresponding symbols are different. So these strings could be like from our alphabet, or they could be strings of zeros and ones or whatever. They could be any kind of strings, as long as everything we're interested in is of the same length. So for example, the distance between the names Carolyn and Catherine, spelled in that way, would be 3, because they differ in 1, 2, 3 points, and all the other elements of the string are the same. And as another example, the distance between those 2 strings of 5 binary digits is 1, because they differ in 1 place. So one can prove that this is a metric on the set of strings of length n, and this Hamming distance has various applications, such as error detecting and correcting codes. Here is a new definition. Let's let xd be a metric space and A be a non-empty subset of X. So if the set of distances between X and Y, such that X and Y are in the set A, has an upper bound, then A is called a bounded set, and the diameter of A is given by capital D of A. The diameter of A is the least upper bound of the distances between X and Y, such that X and Y are in A. For completeness, we define the diameter of the empty set to be 0, and if the set X is bounded, then we call the metric space XD a bounded metric space. So as a quick example, if X is the set of strings of length n, then the set X with the Hamming distance is a bounded metric space, since the diameter of that set would be n. So if there's only n bits in each string, then there can be at most n places in which 2 strings differ. Here's another example to try. Consider the set A being the open interval -1, +1, crossed with the open interval from -1 to +1 as a subset of the real numbers squared. Then what is the diameter of A in these other metrics we've been talking about? The usual metric, the taxicab metric, the max metric, and the discrete metric. So pause, try those out, and we will talk about them in a moment. Okay, so here is a graphical representation of our set A, the open interval from -1 to +1, crossed with the open interval from -1 to +1. Because this is an open interval, I've drawn sort of dotted lines along the edges. So what is the least upper bound of the distances between points in this set? So, if we think about points that are as far away as possible from one another, they would be kind of points at, one corner to another corner. And we know that the actual endpoints are not included, but because this is the least upper bound, we do have an upper bound on that distance. So in the usual metric, that upper bound would be the distance, say, between the points 1, 1 and -1, -1, or on the other side similarly. That would be the least upper bound of the distances between these points, or between points in this set. And so in the usual metric, that's just the length of that hypotenuse. So this diameter of A is going to be the square root of this distance here is 2. The distance in Y is also 2. So 2 squared plus 2 squared, that's going to give us the square root of 8, which is also 2 times the square root of 2. So in the usual metric, the diameter of this set is 2 times the square root of 2. How about in the taxicab metric? So in the taxicab metric, then we're also only thinking about this, Manhattan distance going along a grid. And so the distance, the diameter of this set then, again, the least upper bound of distances between points in that set is going to be 2 plus 2, it's going to be 4. So the diameter of this set in the taxicab metric is 4. In the max metric, again, we still sort of have the same idea of, what's the maximum distance in each of the possible coordinates, and in each of possible coordinates, the least upper bound for those distances is going to be 2. So d of a, the diameter of a in this metric is 2. And in the discrete metric, if we take any pair of points that are not equal to each other, then we know the distance between those 2 points is defined to be 1. If the points are the same point repeated, the distance is defined to be 0. So there is an upper bound, and the diameter in the discrete metric is 1.